There we go. Thanks, Jordan. All right. So we're in chapter.
Yeah.
So our approach is going to be slightly different than the textbook. The material is identical. The difference is this. So in chapter 8, what we're doing is we're going to start to look at second order circuits, okay? So we're going to start to look at second order circuits. And in order to do that, we have to understand some things about second order differential equations. But the second order circuits that this author and many authors of circuits textbooks restrict themselves to because they're easier are the series RLC circuit and the parallel RLC circuit. So they're very highly restrictive to only two types of circuits. I know why they do that, because those circuits are much easier to solve than general circuits. But we're not going to do that restriction. We're not going to restrict to just those circuits. We're going to look at all circuits. In order to be able to work with those circuits, we need to understand the mathematics behind what we are going to encounter. And so to that end, what we're going to do is look at what I call second order constant coefficient differential equations. DEQ stands for differential equation. I'll continue to use DEQ, but here as a reminder, DEQ is a differential equation. We've already seen a first order differential equation, so we know what differential equations are. They are equations in the variable that involve derivatives. First order derivative, second order derivative, third order, fourth order. That's a differential equation. So we have dealt so far with, we've seen these first order equations that look like this. dx dt plus ax equals capital A. And we restricted it up to this point, restricted this to DC. We're going to expand beyond that. Restrict that to DC. It doesn't have to just be a constant value anymore. So it'll be restricted beyond DC. So these are the equations that we're going to look at. They're going to look like the following. So I'm going to write it this way first. D squared dt squared of x plus a1 of dx dt plus a0 times x is equal to any function f of t. Notice it's not just restricted to a constant anymore. Because it's cumbersome to continue to write ddt's all over the place, I'm going to drop that notation. So those of you who have taken physics courses may have recognized this notation. So it's a notation that's used when derivatives are with respect to time. So a time derivative can look like the following. So x dot dot. So the derivative, the double dot means two derivatives, and the dot implies it's a derivative with respect to time. Plus a1 x dot plus a0 x is equal to f of t. I'm not going to use that notation. I'm going to use a notation that's generally used for any type of derivative at all, whether it's a derivative with respect to x, a derivative with respect to y, a derivative with respect to t, a derivative with respect to theta, it doesn't matter. And that is this notation, x double prime, second derivative, plus a1 x prime plus a0 x is equal to f of t. So I'm going to use the prime notation. Every time you see a prime, it's another derivative. We use the prime notation when we dealt with our superposition. That prime notation did not imply a derivative. So here it implies a derivative. So this is the equation that we're looking at, and this is a second order constant coefficient differential equation. These are the coefficients. By the way, this coefficient is 1. It's not written there, but we want our coefficient of the highest derivative to be 1. When it's not 1, we will simply divide through the entire equation by whatever that number is. For example, if this was the number 3, I would divide everything by 3, and I would end up with an equivalent equation that looks like this. Still, a constant coefficient differential equation. constant, constant over here. Okay? Somebody join us or did somebody fall off on us? Okay, so what is true in this equation here is A1 and A0 are real constants. We love that. We like dealing with reals. So our constant coefficient differential equations are going to have coefficients that are real. Bizarre, crazy things can happen when those coefficients are allowed to be complex, but we're not going to be in the complex world right now. The work that we're going to do is going to lead us to the complex world, but not right now. So right now, everything's restricted in terms of those numbers to being real. Now, this is what we know. And those of you who have taken this in differential equations recognize this already. Those of you who haven't just have to believe me. The solution to this equation is the following. So the solution has two parts. One part we'll call x sub h, and the other part x sub f, and we'll describe what those are. So overall, the solution looks like the following. X is the solution, that's what we're solving for. So remember, up here, solve for x, that's what we're doing. Now remind me, in our circuit theory, instead of x, what are we going to have there instead of x? What's going to be in its place? Instead of x, x prime, x double prime, what's that going to be?
Would it be J?
Say that again?
Would it be J?
Nope, it is not J.
I.
Not I. It could be I, but what else could it be?
V.
Yes. All voltages and all currents. That's what they're going to look like. So here, X looks like this. X sub H plus X sub F. So it's a combination. This is the solution. There are two parts. And so we're going to have to break this up and look at how to find each of those parts. But in general, for us in this course, what this is going to look like is it's going to look like, instead of X, it's going to be like I1 equals I1H plus I1F, or VA equals VAH plus VAF, okay? So for us, we're looking at currents and voltages. I'm just using X from the general mathematical notation that all of you are used to, because in your math classes, you use X all the time. You don't use I's and you don't use in V's in your math class. You tend to use X's and Y's all the time. All right, let's define these parts. So X sub H. X sub H is called the homogeneous response. There are other words that are used for homogeneous response. So these are other words. In place of homogeneous, we can use natural. So in some books that you read, they're going to call it X sub N for natural. It is also called the unforced response, or also called the force-free response. Okay, all of these three words can be used in place of homogeneous. And I am going to use them interchangeably, but largely I will use the natural response or the homogeneous response. In general, I will restrict my conversation to this one or this one, and I'll use them interchangeably. And so you should get comfortable with that. X sub F is called the forced response. But there are also other terms for the forced response. And many of you in your math course will remember using the complementary solution. I don't like that. You'll never hear me use that. Or you may have heard the particular response. So those are other words that are used. In this class, I'm going to always call it the forced response. Okay? back to our equation. Let's write our equation back down again now. So we have x double prime plus a1 x prime plus a0 x is equal to f of t. So this f of t is called the forcing function. And it is easy to confuse the forcing function with what most people think. Most people think the forcing function is the source that is in the circuit. All I'm going to say is the forcing function is a function of the independent sources. So when we look at f of t is going to be related to the independent sources that are in the circuit, but we don't know exactly what it's going to be. So the forcing function will always be a function of the independent sources in the circuit. For example, I'm not going to solve any circuits right now. Let's just pretend this is a source in the circuit, okay? And I've got some things going on over here, and I've got a resistor and a capacitor like this, and maybe we're looking for this voltage across the capacitor, okay? So we'll end up with an equation that might look like the following. V double prime plus some number, I'm making it up, 3V prime plus 2V is equal to, and then we're going to get something over here. Whatever we get over here is going to be a function of whatever is over here. So let's just pretend this is e to the minus 6t. E to the minus 6t. Let's put the t up there. In a second, let me just erase that down there. Okay, this will be a function of 3e to the minus 6t. And that function might look something like this. It might be the derivative of 3e to the minus 6t plus 2 times 3e to the minus 6t. That's a function of it. So we don't know exactly what we're going to get. The circuit and the voltage or the current that we're looking at is going to determine what it will be. So you're ready for this? This is going to be really, really interesting. If I looked at this voltage and then over here now, let's call that V1. If I looked at this voltage, call it V2. If I looked at this current, call that I1, or this current I2, or this current I3. You want to know what's really cool about this? In this circuit, every one of those, every current and every voltage will look exactly like this. I1 double prime plus 3I1 prime plus 2I1 equals, and this will be a different function over here. I'll call it G of t. So I1 will have the same exact coefficients as every voltage and every current in the circuit, with the exception of the dependent sources. So you got to love that. It's really cool. So we know something really important, and that is that the circuit itself, all of the components that are in the circuit, describe what this will be. If you change any component, if I change this capacitor, let's say it was a 3 farad capacitor and I changed it to a 2, that 2 is going to affect these coefficients over here. And it'll change them for every variable in the circuit. All right? So far, so good? Now, let's indicate some important information about the homogeneous response. So for the homogeneous response, what is true is X sub H will satisfy the following. It'll satisfy the homogeneous equation. What's the homogeneous equation? The homogeneous equation is when we set the forcing function equal to 0. So it's going to satisfy this plus A1XH prime plus A0X, oops, not H, don't get ahead of yourself. A0X equals 0. This is called the homogeneous equation. So later on in your world of higher education, when you hear people talking about a homogeneous equation, it always means that that equation is set equal to 0. That's the homogeneous equation, when it's set equal to 0. So you can see why this is called the force-free response. If this is this side of the equation and it is a function of the independent sources, then this means perhaps there are no independent sources. So this is the force-free response in this homogeneous equation. So this is an important equation that X sub H satisfies that. Okay? For the forced response, this is going to sound stupid, but for the forced response, X sub F satisfies XF double prime plus A1 XF prime plus A0 XF, and I missed an H up here. I missed that H, please get that H in there. Down here, back to my original equation, equals F of T. What? That's weird. That looks like the original equation we had, except I replaced X by X sub F. It is the original equation that we had, and I did replace X by X sub F. So the forced response is going to satisfy that. Well, wait a minute, then doesn't that mean X sub F is the total response? No, you'll see why. So now my claim. I claim the following. If XF satisfies the equation up above, is the forced response. And XH is the homogeneous response. Then, big then X equals XF plus XH, doesn't matter what order I write those in, is also a response or a solution to the following differential equation. And I'm going to prove that to you. So not only is XF a solution to this equation, but X, which is both of them added together, is also a solution to the equation. So the total solution, we call this the complete response. So the complete response is X equals XF plus XH. That is the complete response, okay? And so we want the complete response. It's not enough to just have XF. It's not enough just to have XH. We want the complete response. All right, so here we go. Let's prove that. So we know X double prime plus A1 X prime plus A0 X is equal to F of T. That's what's supposed to be true. So now I'm going to substitute. So I'm going to substitute this into the equation. We claim it's a solution, so let's see and prove that it is. Okay, so X double prime is XF plus XH double prime plus A1 XF plus XH single prime plus A0 XF plus XH, and this is a question mark. Is that equal to F of T? I claim it is. I claim it's equal to F of T. So now what I'm going to do is I'm going to expand. So remember from your calculus, the derivative of a sum is equal to the sum of the derivatives. So this first term is nothing more than xf double prime plus xh double prime plus a1. Now, again, I have a sum of the derivatives. So this is xf prime plus xh prime. And then finally, the last terms here, a0 xf plus a0 xh. Is that equal to f of t? All right, I'm just going to expand and multiply through here. So that's easy to do. Plus a1 xf prime plus a1 xh prime plus a0 xf plus a0 xh equals f of t. And now I'm going to group all of the terms that have xf's together, and I'm going to group all of the terms that have xh's together. There's an xf term, there's an xf term, there's an xf term. Here we go. xf double prime plus a1 xf prime plus a0 xf. I'm just going to group those. Plus, I'm going to group the other three. xh double prime plus a1 xh prime plus a0 xh. Is that equal to f of t? To determine whether or not it's equal to f of t, I want you to look at this right here. And I'm going to scroll up. So look at it, xf double prime, you've got it in front of you. I'm going to scroll up. What is xf double prime plus a1 xf prime plus a0 xf equal to? What is it equal to?
F of t.
F of t. So down here, I'm going to put that. That's f of t. Look up at your notes and see what this one is equal to. What did we say it was equal to for xh? I'll scroll. Here it is for xh. What's it equal to?
0.
0. Is f of t plus 0 equal to f of t? It sure is. So we need both of those pieces to get the complete response for x. We can't just have the forced response. We need the complete response. I want you to know that everything that we talked about in those first order circuits, when we were looking at the forced response was the DC steady state that response, the one that lasts for a long time, that hangs in there. That had been our forced response before. And the homogeneous response was the part that died out. So we want to spend a good amount of time looking at the homogeneous response or the natural response. We want to spend a good amount of time doing that. So let's do that. Any questions so far? Anybody lost yet? I'm going to remind you what I've been reminding you all semester long. For those of you who are not strong on your calculus, don't worry about it. We're getting to a result, and that's what I need you to know. I need you to know the result. That's what I need you to know. So we're getting there. We're not there yet. All of this is the mathematics behind the scene to help you understand. All right, so the natural response, we know it satisfies the following. So XH satisfies XH double prime plus XH prime, A1 XH prime plus A0 XH. Don't forget, those are just numbers, and that's going to be equal to 0. It satisfies that. So what we've got to do is we've got to rely on, in this course, we're not relying on all of our mathematical background, but we're going to rely on some ingenuity of some things. So rather than using math to solve this, I'm going to rely on our expertise and our knowledge of calculus. All right, so I'm going to write that down. I'm going to rely on our knowledge of calculus and mathematics. Well, what do I mean by that? Let's look at this equation, because this is weird. For those of us who really have not had a lot of calculus, this is an interesting equation. So this is what it says. I take a function, if I take a function right here, and I multiply it by a constant, and then I take the function's derivative and multiply it by a constant, and then I take the second derivative of that function, and then I add all those three together, they're equal to 0. That tells me something about the function. And right now, I just want you to think of some functions. So anybody give me a function. Any function that you're used to using. So let's let a function, I'm going to define it to be equal to, and I'm going to wait on somebody going to give me a function so you can tell me what function you want me to define this to be equal to. It's either we have no idea what functions are, or this is too trivial. I'm going to assume that it's not, that it's too trivial. I'll make up a function. You ready? I'm making up a function. The natural log of x. That's a function. What's the derivative of that function? What's the derivative of the natural log of x?
The log function?
Nope, it's not the log function. Derivative of the natural log. Do you remember the derivative of that function? 1 over x, which is x to the minus 1. And so therefore, the second derivative is equal to minus 1 x to the minus 2, which is equal to minus 1 over x squared. I just want you to look at these three. I want you to look at them. And I want to look at if we substitute them into this equation. So this is what I would have. Minus 1 over x squared plus a1, a constant, don't forget, a constant times 1 over x plus a0, another constant, times the natural log of x is equal to 0. This has got to be true for all values of x. How in the world can negative 1 over x squared be added to some constant like 3 plus 3 over x plus a0? How can that be equal to 0? The answer is it can't be. So what we need to consider, the problem here is this form is different than that form. It's different than that form. The only way that this can be true is if the derivative has a form that looks exactly like the function we're taking the derivative of. That's the only way it's going to work. So I have to think of functions. So what functions can you think of? Function or functions have a derivative that have the same form as the function itself. Hint, we've been seeing this in this course for quite some time now. What functions can you think of that have a derivative that look exactly like the function?
E to the x.
There you go, e to the x, it's exactly right. So since we're in the world of t, we know the following. So we know that x sub h must look like an exponential function. Because the derivative of an exponential, when I take the derivative, I get e to the st back. You might argue that could also be a cosine or a sine function, because derivative of the sine is the cosine. But we know a cosine is related to a sine, so we know they're the same function, just shifted. But I'm going to remind you the sine and the cosine are exponential functions. Remember that from Tuesday? They are exponentials. So don't worry about that. This must be the form. So x of sub h must look like that. All right. So xh equals k e to the st. xh prime equals, every time I take a derivative, an s comes down out front. So it's going to be k s e to the st. And then the next derivative is going to, another s is going to come down. So xh double prime is k s squared e to the st. And what we don't know is we need to figure out what value of s is going to make this work. Need to determine the value or the values of s that will satisfy the differential equation. In this case, it's the homogeneous differential equation, right? The homogeneous equation. All right. So let's hold that right there. So here's our differential equation. Just a reminder. At xh double prime. This is the problem with being left-handed, by the way. The left hand, when you write, unfortunately writes all over everything. Or it moves over everything. Let's get this blown up a little bit larger. Okay. xh double prime plus a1 xh. In particular, my fingers are on that little house that you see in the top corner. And when I go to that house, it takes me back to that page that you just saw. Plus a0 xh equals 0. So this is the equation we're looking at. Okay, now I'm plugging in. Here's the second derivative right up there. I'm going to plug that in. K s squared e to the st plus a1 xh prime, this one right here, k s e to the st plus a0, and then the last one, k e to the st. It's equal to 0. Now from here, believe it or not, it gets pretty easy. So I'm going to factor out a k. There's a k in every one of those terms. I'm going to factor it out. There is also an e to the st in every one of those terms. I'm going to factor that out. And then I have s squared plus a1s plus a0. And all of that is equal to 0. Okay. We're almost home. This is a product. This times this times this is equal to 0. So one of the following three things must be true. One, k is 0. 2, e to the st is 0. 3, s squared plus a1s plus a0 is equal to 0. Everybody agree with those three? Or does anybody disagree with those three? Since everybody's shy and doesn't want to chime in. Let's look at the first one. K is 0. If k is 0, xh equals 0. How many of you already knew that if xh was equal to 0, then its second derivative plus a1 times its first derivative plus a0 times 0? How many of you already knew when I took this in, 0, and I substituted into this differential equation, that we'd end up with a 0 there, the derivative of 0 is 0, the second derivative is 0, and therefore 0 is equal to 0? I think every one of you knew that already. This is called the trivial solution, and we have zero interest in the trivial solution. In other words, the trivial solution, xh equals 0. And that doesn't give us any new information. So that's not interesting. Let's look at the second one. Remember, we're solving for s. We want to know what value of s. So when is e to the st equal to 0? It needs to be 0 for all t. When is e to the st equal to 0? When s is equal to what?
Infinity.
Excellent. When s is equal to minus infinity. But we don't deal with minus infinity as a number, so therefore, there is no solution. Okay? There is no constant value of s in which e to the st is equal to 0. There is no constant value. Negative infinity is a good value, but then somebody might argue, well, wait a minute, when s is equal to negative infinity and t is equal to positive infinity, how does that work? Or what about when t is equal to negative infinity and s is equal to negative infinity? Multiply those two together, that's negative twice infinity, right? It's infinity squared. So that doesn't work. So then the bottom line is we're left with number 3 as our solution. And all of you know that this is a quadratic equation. And there are 2 solutions for s. So there's not just one, there are 2 solutions for s. So let's look at that. So we call this equation is so important, it gets a name. So s squared plus a1s plus a0 equals 0 is called the characteristic equation. It's called, let's get a the in there. And it is characteristic of the circuit elements that you have. Not so much the sources, more than the sources, it is characteristic of the elements in the dependent sources. So it's called a characteristic equation. And we know how to solve this equation because it's nothing more than the quadratic formula that allows us to solve for that. So let's just pause for a moment before we get to that and just get an example. Watch how easy it is to get the characteristic equation, because remember where A1 comes from and remember where A0 comes from. So here's an example. I double prime plus 4I prime plus 3I is equal to 12 cosine of t. So the first thing I want somebody to do is I want you to tell me what is the homogeneous equation, even though I don't even need to write this down. What is the homogeneous equation? I know somebody out there knows. I know several of you have taken differential equations. I just take the same equation, I copy it over here, I replace that with 0. I put the subscript h on so that those i's have a subscript showing that it's the homogeneous term, and then all of these numbers that we have, they all copy over. All of those coefficients just copy right over. So the coefficient 4 copies over to the first derivative, the coefficient 3, copies over to the 0th derivative term. Okay? Everybody good with that? Anybody not understand that? I'm not hearing anything. Let's take a pause, a little check on the temperature out there. How are we doing with all of this?
I'm good.
Okay, so Jack, you're on this. You've seen this in your course, right?
Yeah, I'm good.
Okay, we're good there.
I'm good.
Outstanding. Very good. So far, so good. I've got a lockup on my pad right now. So why don't we do this? I'm going to try to unlock this pad. Why don't you take a 5-minute break? I'm going to give a 5-minute break. I think we need breaks now. I've observed this over the past 2 lectures that we've had. We need a little break. So let's go on break, okay? And then we'll come back in 5 minutes. And hopefully my pad will have unlocked, or I'm going to work on it to unlock it.
Hey. Come on.
Okay, are we here? Are we ready to roll?
Yep, ready to go.
Okay, good.
Ready to go.
Excellent. All right. So we're gonna continue now. I've had to shut my Surface Pro pad down and then reboot it. And fortunately, it saved everything that I had on the white screen. So we've got all of that information and didn't lose any of it. So we're just going to pick up right where we left off here. So right now we were looking at a particular differential equation that I've randomly put some numbers in. I've just used those numbers as numbers so you can finally see something that has numbers in it. But what I'm looking at is I want to know, how do I immediately go from this differential equation to the characteristic equation? And the answer is it's as simple as this. Everywhere you see a double derivative, just take it down, and it's every derivative is a power of s. Plus, the 4 comes down, 4. First derivative, s to the first power, plus 3. No derivatives, s to the 0 power. We know s to the 0 power is 1 equals 0. There it is. That is the characteristic equation. So how easy is it to find the characteristic equation once you have the differential equation? All of our hard work is going to be getting the differential equation from the circuit. Once we're there, then it's just mathematical crunching. This one is really easy. So getting this is really easy. Okay. Now, when we look at this, we know that there are 3 different forms that the solution to this characteristic equation is going to take on. Most of you know, I think every one of you knows, the first thing that we would do with this is we would do the following. We'd factor this if we could factor it, or we'd use the quadratic formula if we don't know how to factor it. So we'd factor this one. This one's pretty easy. S plus 3, s plus 1 is equal to 0. And we know, therefore, that s is equal to minus 3 and minus 1. There are 2 solutions, and there it is. There are 2 solutions. Why are there 2 solutions? Because it's a second-order differential equation, which comes from a second-order circuit. The circuits that we've dealt with up until this point have been first-order circuits. And you'll notice that we only got 1 exponential in the homogeneous response or the natural response. There was only 1 term that was there. Now we get 2 terms. So with 2 terms, some bizarre things can happen. So let's take a look at what those bizarre things are. So let's look at the natural frequencies. So what are the natural frequencies? By definition, the natural frequencies are the values of s that satisfy the characteristic equation. So these are the values of s that satisfy the characteristic equation. My apologies to all of you people who love your math class better than your circuits class, because you know that in your math class, you don't use s. What variable do you use instead of s in your math class?
X.
No, this is for, in general, Jordan, you're right. You would use x here, but I'm talking in particular for the differential equation when you're looking at the homogeneous response. So you wouldn't know that because you haven't had a differential equations course. So Jack or Connor, you have, what is that variable?
Be A.
I think it's M, yes? Didn't your math textbook use M for that variable?
Yeah, we use them.
Okay. M. So we use S, and in your differential equations course, you used M. S is the same S. You'll love this. For those of you who have had this, it is the same S for the Laplace transform. That's why we're using S. It is a frequency. It doesn't look like it's a frequency. It's a frequency. So we call them the natural frequencies, and they are the values of S. And the way we find it from the differential equation, from the differential equation is we go from the differential equation to the characteristic equation, which looks like this: S squared plus A1S plus A0 equals 0. And then we find the solutions based on the quadratic formula. S equals minus A1 plus or minus the square root of a1 squared minus 4a0, all divided by 2. The important part to us is what's underneath the radical sign. Some of you know that as the discriminant. So the discriminant is a1 squared minus 4a0. And there are 3 things that can happen to the discriminant. So we have 3 categories. Category 1. In category 1, the discriminant is greater than 0. So we're taking the square root of a positive number. We love that. That's the world we live in. So a1 squared minus 4a0 is greater than 0. We call this real distinct roots. The roots are real and they are distinct. That is, S1 is not equal to S2, so they're distinct. They are both different from each other. And S1 and S2 are reals. And that would be this example right here. Here's S1, there's S2. They are both real numbers and they are not equal to each other. So S1 and S2 are real and they are not equal to each other. That's category 1. And we'll come back and describe some more about that. Category 2. a1 squared minus 4a0 is equal to 0. So when the square root is equal to 0, you can see, can't see it right now, but you will see in a moment. There we go. You can see that when this is 0, it's minus a1 plus and minus the square root of 0. Minus a1 plus and minus 0. I'm going to get the same thing for both answers. So we call this real repeated roots. So what we have is S1 is equal to S2 this time, and they are both, obviously, they're both the same thing. So S1, which is equal to S2, is a real number. And then finally, we have category 3. And this is why we spend so much time on complex numbers. And so category 3 occurs when a1 squared minus 4a0 is negative. So when we get a negative sign underneath the radical, we're taking the square root of a negative number, and we know that that is purely imaginary. Okay, what's underneath this here is negative, so the square root of it, the square root of a negative number, is going to be j something. J something, square root of a negative number. So I have a real number plus or minus j something. Oh my God, that's called a complex number. Unbelievable. So what we have there is that we have what are called complex, but they're going to be complex conjugates. Why are they complex conjugates? Because one is plus the square root, so it's going to be plus j, and the other is minus the j. So they're complex conjugates of each other. So this time what we have is S1 and S2, S1 comma S2. They are complex conjugates. I'll write it this way first, though. They are complex conjugates, so I'm going to write it the following way. S1 equals S2 conjugate, or S2 equals S1 conjugate. They're the conjugate of each other. And at the same time, S1 and S2 obviously are elements of the complex number system. So they're complex. So usually we're not really fond of running into complex numbers, but we're not going to let any of that bother us. Let's do some examples. let's assume that we just have that s squared plus 6s plus 5 is equal to 0. So the first thing you should always do is you should always see if you can easily factor this with whole numbers, and you can. S plus 5 times s plus 1 is equal to 0. Therefore, s plus 5 equals 0 or s plus 1 is equal to 0. That means s is equal to minus 5 minus 1. Just to be clear, in case you're not good at factoring, s, 1 and 2 are equal to minus 6 plus or minus the square root of 6 squared minus 4 times 5, all divided by 2. That's equal to minus 6 plus or minus the square root of 36 minus 20, square root of 16 divided by 2, equals minus 6 plus or minus 4 over 2. So now, taking the plus, that's equal to minus 6 plus 4, that's minus 2 over 2. And minus 6 minus 4 is minus 10 over 2. And you can see that that is negative 1, and that is negative 5. So your answer will always come out using the quadratic formula if you feel like you're not very good at factoring. So that's an example of real distinct roots. Let's look at an example of real repeated roots. S squared plus 4s plus 4 is equal to 0. Again, if you're good at factoring, s plus 2 times s plus 2 is equal to 0. And obviously, s1 and s2 are both equal to minus 2. You can check that out using the quadratic formula. If you do, you're going to get the following. s12 equal to minus 4 plus or minus the square root of 4 squared minus 4 times 4, all divided by 2. You can see that that's obviously equal to 0. So it's equals minus 4 plus or minus the square root of 0 divided by 2. So minus 4 minus 0, minus 4 plus 0. Both of them are minus 4 over 2. Both of them. Both answers, minus 2. Then the not so nice ones, the complex conjugates. So in this example, s squared plus 2s plus 5 is equal to 0. Some of you might be really good at factoring. I'm pretty good at it, and I know the following. This can be factored into s plus 1 plus 2j times s plus 1 minus 2j is equal to 0. So that tells me s equals minus 1 minus 2j, that's for the first one, and minus 1 plus 2j for the second one. Remember, this number is always the negative of this number. It's always the negative of this. Okay? So let's just show that by using the quadratic formula. So we're using this equation, the quadratic formula, S12 are equal to minus b, minus 2, plus or minus the square root of b squared, 2 squared, minus 4 times a, which is always 1, times c, all divided by 2 times a, but a is 1. This is minus 2 plus or minus the square root. You can see how I have 4 minus 20, that's minus 16 divided by 2. If you're a little rusty, just remember the square root of minus 16 is the square root of minus 1 times the square root of 16. Okay, there's the j. Square root of 16 is 4. This is equal to minus 2 plus or minus j 4 over 2, which is minus 2 over 2, that's minus 1, plus or minus j 4 divided by 2. 4 divided by 2 is 2, plus minus j2. And those are the two answers that we have there. Minus 1 minus 2j, minus 1 plus 2j. So that's an example of what we're going to be running into. Once we find the differential equation, we will immediately go to the characteristic equation. and then we'll take the characteristic equation and we'll immediately calculate the natural frequencies. And there they are. These are the natural frequencies. Now, what might be confusing right now on this last one, maybe, is don't forget, this is the value of S. So that goes in there. It goes up there in the exponent. Oh my goodness. E to, for example, -1 plus 2j times t. Wow, that's kind of weird. How do we deal with that? Question mark. Don't worry about it. We'll tell you how to deal with it. Okay, so those values are called the natural frequencies. Those values of S are called the natural frequencies. Now, I'm going to show as little as I need to show on the following. So given that we have real, distinct roots, the form of the homogeneous response is, okay, so we have, just remember, S1 is not equal to S2, and they are both real. So the form of the response is XH equals, and you just need to know this, K1 e to the S1t plus K2 e to the S2t. So each individual S is a solution to the homogeneous, to the exponential value of the homogeneous equation. But when I add them together, they are both the solution. They are both the solution. Let's do an example and stop right here so you can completely understand. There we go. Example. Only a homogeneous response right now. X double prime. So plus 5x prime plus 6x equals 0. So first, note the differential equation is only a homogeneous equation. There is only a homogeneous response. There is no forced response. The forcing term is 0. So there's only a homogeneous response. So here's what we do. The very first thing we do is go right to the characteristic equation. S squared plus 5s plus 6 equals 0. We immediately go to that. Now we solve. S plus 2 times S plus 3 is equal to 0. So S equals -2 and -3. So we have our two values. Therefore, the homogeneous response is X sub H equals K1 e to the -2t plus K2 e to the -3t. That is the solution. That is the homogeneous solution. And it will be the full solution because this is only a homogeneous, it's only a homogeneous differential equation. So that's how easy it is. All that work we did just to tell you that's the answer. Now, some of you might not believe me. So here's what I'm going to do. I'm going to do a check here. So in this case, I'm going to check by knowing the following. XH equals K1 e to the -2t plus K2 e to the -3t. I need its derivative. First derivative, -2K1 e to the -2t -3 K2 e to the -3t. And I need its second derivative. Equals. Again, every time another -2 is going to come down. That's going to turn that into 4. K1 e to the -2t plus 9 K2 e to the -3t. Just want to remind you, this is S down there. There's an S squared there. This is S2. There's S2 there. And there's S2 squared there. So just a reminder that everything that we showed before is still going to hold true. Now we have to check this in the differential equation. So now I'm going to substitute it into the differential equation. XH xh double prime plus 5xh prime plus 6xh. Is it really equal to 0? Is it? Let's check. 4k1 e to the minus 2t plus 9k2 e to the minus 3t. That's that term, plus 5 times minus 2k1 e to the minus 2t minus 3k2 e to the minus 3t. Notice, just like in the first order, this works for all values of k right now. Plus 6 times xh, k1 e to the minus 2t plus k2 e to the minus 3t. And the question is that equal to 0? All right, here's what I'm going to do for you right now. I'm going to group the e to the minus 2t terms. So let's see if you agree with this. I have 4k1 minus 2k1, but don't forget that multiplies 5, minus 10k1 plus 6k1, and all of those multiply e to the minus 2t. Let's get the e to the minus 3t terms. This one, and this one. 9k2. Don't forget this minus 3 is still multiplied by that 5, minus 15k2. This k2 over here is multiplied by that 6, plus 6k2 e to the minus 3t. All of this came from the e to the minus 3t terms, so you can see how everything inside of parentheses is equal to 0. You can see how everything inside of this parentheses is equal to 0. So indeed, it's equal to 0. And I'm not gonna go ahead and prove that for all of these, but I just want you to show the one term, this term by itself satisfies the homogeneous equation. This one by itself satisfies the homogeneous equation. And when I add them together, since they're both equal to 0, 0 plus 0 is still equal to 0. So both of them work, and that satisfies the differential equation. And that is true for all K1 and K2. Now for us, K1 and K2 are going to be real, but it works for complex K1 and K2. It works for all K1 and K2. No restrictions. All right, let's take a look at an example of category 2. So this is real repeated roots. So before I go there, oh gosh, my screen is freezing again. Don't do that on me. I think it might be getting too hot. So up here, let me remind you that this situation here, tell you, I'm not going to remind you, I haven't told you yet. So we call this situation, category 1, real repeated roots, is called critically damped. You don't know why it's critically damped. I'm telling you, it's called critically damped. So when we have real repeated roots, we have a critically damped situation. Who checked in? Is that Lena?
Oh no, that was Terrence.
Okay.
I got a call and it kicked me out. Sorry.
So yeah, that's okay. I'm just making sure we're all okay. So this is called the critically damped situation. Critically damped corresponds to category 1. What is category 1? It is real distinct roots. That is critically damped. Every time it happens, it's critically damped. Before I go to category 2, let me just erase this for a moment. Before we go to category 2, does anybody have any idea if we were to sketch this, what this might look like? Like what does, so we know that XH equals, we'll pick any value, it works for any values of K1 and K2. So you can pick any value you want to. But K1 e to the minus 2t plus K2 e to the minus 3t. Like, what does that look like? Well, gosh, we know what each of these individually looks like. just pretend K1 and K2 are positive numbers. I know we don't know what they are. K1 e to the minus 2t does this for t greater than 0. So that will be K1 e to the minus 2t. K2 e to the minus 3t, depending upon the value of K2. Let's pretend K1 and K2 are the same. Okay, so let's pretend they're the same. They don't have to be, but just right now, for purposes of illustrating what's going on. E to the minus 3t decays faster. So it does that. And then we're just going to add those two together. What does that look like? In general, especially when there's a significant difference between the decay rates, what happens is one of them is going to hang around a lot longer. And basically, if you had something like this, like one decays real rapidly like this, and the other one does something like this, in general, you get more of a spike here, but then it tends to look like that. Okay? So what does it look like? It tends to look like at the end out here over time, it tends to look like the decay of the slower decay rate. That's what it looks like. All right, so that is our critically damped situation. I'm sorry, did I write critically damped? Gosh, critically damped is for what I'm going to do. Please erase that. Call Dennis an idiot for not paying attention to what he's doing. This is the overdamped. Overdamped. All one word. Okay, this is the overdamped situation. I apologize for that mistake. I was focused on where I was going to. So now, in category 2, just a reminder, this is the real repeated roots. And this is called the critically damped case. You're going to try to make rhyme or reason out of the terminology overdamped, underdamped, and critically damped. You're going to try to make reason out of it. But don't try, because it's not logical from the perspective that we're looking at right now. So right now, they're going to be overdamped, underdamped, and critically damped. That's what we're going to have. And we're just going to deal with it in terms of that terminology. I want you to know the terminology. I also want you to know I'm not going to test you on the terminology. I want you to know it, but I'm not going to test you on it. Okay. In the critically damped case, what we have is the following. The solution will be of the form. So remember, in this case, real repeated roots, S1 equals S2. I'm just going to call it, for argument's sake, I'm just going to use S1 because S1 and S2 are the same, so it doesn't matter. So they are of the form, or the solution is of the form X sub H equals K1 plus K2T. There are many ways to write it. I think you will find this to be the best way to write it, E to the S1T. So normally what we want to do is the following. We always want to take K1 e to the S1t plus K2 e to the S2t, but S1 and S2 are the same. So this would be nothing more than K1 plus K2 times e to the S1t. And that's only one term. There's always going to be two terms for a second order differential equation. So there needs to be a second term. So this is what happens. Anytime you get something funky going on with repetition, with something that's repeated, anytime you get that, we know from mathematics, it means to put in math, it would be an X multiplier. Here, it's a T multiplier. So really what this is, it's K1 e to the S1t plus K2t e to the S1t. I get this t multiplier. So this is the form of the solution. Don't worry about why it's the form. It's the form. All you need to know is it's the form. Let's use that. Now that we know it's the form, let's do an example and see how we use that. Ready? Here we go in our example. Example, x double prime plus 6x prime plus 9x is equal to 0. Okay? That is, again, it is only a homogeneous term. It's only homogeneous because it's equal to 0. So there's only a homogeneous response. So what's the first thing that I do? Well, the first thing that I do is I write the characteristic equation. And this is s plus 3 equals 0. Oh, my goodness, real repeated roots. S1 equals S2 equals -3. Don't forget this, by the way. I know that's 3. This is always the negative of what we get over here. It's the value of S that causes the whole term to be equal to 0. That's why it's negative. Don't forget that. -3 is what causes it to be 0. Okay, beautiful. Now we have that. So we go right to the solution. X homogeneous equals K1 plus K2t all times e to the minus. Notice all we did is we just substituted that number in. All that hard work just to get that. We already know the form of the solution. But the problem is we don't know the form of the solution until we solve the characteristic equation. If you want me to, I will go through the analysis of plugging this in and prove to you in this differential. In fact, let me do that. Let me do that. So I'm going to prove. So I have xh, so I'm going to need xh prime. So the derivative is equal to the derivative of the first, K1 times the second, e to the minus 3t, plus the first, K1 plus K2t times the derivative of the second, minus 3 e to the minus 3t. Let's group all of this together, equals. So notice they all have e to the minus 3t, e to the minus 3t. They all have that. Now I have a K1 here, and I have a minus 3K1 here. So all of that, let's see, 3K1, minus 3K1, first and second. Make sure I did this correctly. K1 to the minus 3T. I did this incorrectly. The derivative of the first, I knew things didn't add up properly when I was adding them. The derivative of the first is K2, not K1. The derivative of this term is K2, right here, not K1. Okay, now I have K1 plus K2, K1 plus K2, and then I still have plus K2t, right? I still have plus K2t. Let's do a big bracket here. So what did happen to my I left my minus 3 outs. Help me, 3K1, minus 3K1. Let me erase this. I'm getting really sloppy right now. I'm getting really sloppy because I'm trying to hold this pad. You can't see me because it's overheating, and I think that's why it's locking up. And I'm not focused on what I'm doing. So let me get focused on what I'm doing. Okay, so K2 minus 3K1. Here we go. Minus 3K1 plus K2. All of that. And then minus 3K2 minus 3K2t. All of that. That's that derivative. Okay? Then if we do the same thing, and it's going to get uglier, so bear with me and correct me when I make mistakes here. The derivative of the first, minus 3K2. So that's the derivative of the times the second, e to the minus 3t, plus the first, this is where it gets ugly, minus 3k1 plus k2 minus 3k2t times the derivative of the second, brings down another minus 3 e to the minus 3t. And we can always group it so that it looks like the first one that we have. So you do the math. I'm just going to tell you right now from my notes here, this is 9k1 minus 6k2 plus 9k2t, all of that times e to the minus 3t. It's always going to be a constant plus a constant times t times e to the minus 3t. Okay, those are the three terms. Now when you substitute those three terms into the differential equation, everything should cancel out. But I want to do that because I want to show you how you have to do the cancellations. So I'm going to substitute them in. Ready? I have x double prime 9k1 minus 6k2 plus 9k2 t e to the minus 3t. Then I have plus 6 times x single prime minus 3k1 plus k2 minus 3k2t e to the minus 3t. By the way, we know this e to the minus 3t is all the way through. We could just pull it out if we wanted to. Plus 9, just regular old x. k1 plus k2t e to the minus 3t. The question is that equal to 0? Okay, here's what I'm going to do. Since they all multiply e to the minus 3t, I'm going to pull out, first, I'm going to pull out the terms that don't have a t multiplier. That one, it multiplies e to the minus 3t. This one times 6 multiplies e to the minus 3t. This one times 9 multiplies e to the minus 3t. So here we go. 9k1 minus 6k2 minus 18k1 plus 6k2 plus 9k1. Okay, those are all those terms. Then I have the terms that multiply the t. Now all of these still multiply e to the minus 3t. Don't worry about that. Okay, they still multiply that. But now I'm going to go to the t terms. That one, and that one. So let's see what we have. So we have plus 9k2. And there's going to be a t outside of this. And then I have this one times 6 minus 18k2. And then I have this one times 9 plus 9k2. All of that multiplies t, multiplies e to the minus 3t. Look at the parentheses terms. Minus 18 plus 9 plus 9. 0. Now, for the k1s over here, here's a positive 9, minus 18, positive 9, 0 on the k1s, minus 6 on the k2, plus 6 on the k2. Zip, zip, 0. No more question mark. Yes, indeed, it's equal to 0. Okay, so we're not responsible for doing all of this and plugging all this back in. We're just getting the answer. We're stopping right here. We get this, and then we get this answer. We stop right there. That's what we're doing. All right, let's look at the last case, which is the ugliest. It's the one that we like the least. And so that is going to be our category 3. That is called the complex conjugate roots. complex conjugate roots. We call this the underdamped. I can help you understand the underdamped. Underdamped, meaning not damped enough. So that's called the underdamped case. And so we know S1 is equal to S2 complex conjugate. We know that. So this is what we're going to write. S1 and S2, different books use different terminology. So I'm going to just say they're complex conjugates. It's going to be alpha plus or minus J beta. All right? So they're complex conjugates. Alpha is a real number, beta is a real number, but overall S1 and S2 are complex. They're alpha plus J beta. Think of it this way, A plus and minus JB. I'm just using Greek letters, A plus or minus JB. Often, many books will use omega here because it is a frequency of a sinusoid. You're going to see that in a moment. So here we go. When we have complex conjugate roots, the solution is X homogeneous is equal to K1 sine of beta t plus K2 cosine of beta t all times e to the alpha t. Now remember, in general, alpha is going to be a negative number. This number is going to be a negative number because if it's not negative, this is going to give us an exponential. So it's going to be an exponential decay is what's going to happen from real circuits. It's going to be a negative number. So the question is, what does all of this look like? So if we were to try to sketch this, it's going to look something like the following. That's what it's going to look like. It's a sinusoidal signal that's decaying away. That's what we're going to get. The decay rate, this rate here, is determined by that value of alpha. The sinusoidal frequency here is determined by this value of beta. So that's what this form looks like, this underdamped case. It looks like that. Questions on any of that? Let's do an example. So in this example, x double prime plus 4, x prime plus 13, x is equal to 0. S squared plus 4s plus 13 equals 0. If you can factor, factor. S plus 2 plus 3j, s plus 2 minus 3j equals 0. A lot of you have not been taught how to do that. If you don't know how to do that, use the quadratic formula. I'll do that with you right here. S, 1 and 2 are equal to minus 4 plus or minus the square root b squared, 4 squared minus 4 times a times c, 4 times 13, all divided by 2. That's equal to minus 4 plus or minus the square root of, you can see how this is 16 minus 52. You can see how you have a negative number under there, all divided by 2. So what's 52 minus 16 or 16 minus 52? 36, is that correct? Equals minus 4 plus or minus the square root of negative 36 divided by 2. And that's going to be equal to minus 2 plus or minus J3. Because the square root of 36 is 6, and 6 divided by 2 is 3. So there's our answers. Minus 2 plus minus J3. Now, what does that mean? Therefore, X of H, the homogeneous response, is equal to K1 sine of 3t. See that 3? Right in there. Don't take the negative. Always take the positive quantity. Don't take the negative value. Plus K2 cosine of 3t, all multiplied by e to the minus 2t. The minus 2 is that number right there. The 3 is there and there. That is the form of the solution. And in all of this, we've left K1 and K2, every value of K1 and K2 works, every value. I'm not going to go through these derivatives. They are uglier to calculate these derivatives because we've got a quotient rule with this term and this term. So work through it, deal with it, okay, with those derivatives. They're not too bad. They're not overly difficult. All right, let's pause here, little temperature check on you. Any questions on finding the homogeneous response? That's just the homogeneous response. You know what's really funny about that? That's the part of the response that disappears. It goes away. It doesn't even hang around. And we spent all that time just trying to find that one. A forced response should be much more interesting. So any questions on that? I'll just unmute my video. Everybody comfortable? You understand how quickly you can get that? Given the differential equation, look at the left-hand side of the differential equation. Replace every derivative with a power in the exponent of s. So you're going to replace whatever the variable is. If it's v, replace v. If it's I, replace I. If it's x, you replace x with s. Then for every derivative, if it's 3 derivatives, it's s cubed. 2 derivatives, s squared. 1 derivative, s to the first power. 0 derivatives, s to the 0 power, but s to the 0 power is equal to 1. So we just replace all of those with the s's. And then we bring the coefficients right down. So whatever coefficients we have, we bring them down. Set it equal to 0. That's a quadratic equation. Solve that quadratic equation using the quadratic formula or factor. I will try very hard to give you things that factor nicely, but we are going to run into situations that are in this underdamped case. And when we do that, and we run into the underdamped case, what's going to happen is you're going to unfortunately get some ugliness in there. And so sometimes it doesn't work out real nice that you can factor it in your head because most of you don't know how to factor numbers that are complex numbers. Okay, comments on that? Any comments? Okay, looks like we're doing okay. So this is what I want to do then. I want to move forward and I want to start talking about the forced response. Because really, this is what is pretty important to us. The forced response. Okay, so the forced response, we're going to use a step-by-step process to figure out the forced response and to figure out the total response. But in the forced response, this is what we know. So we have x double prime plus a1x plus a1x prime plus a0x equals f of t. So f of t is our forcing function. So again, f of t is the forcing function. Okay, so because we know that not everybody, and the writers of these books know that all students have not taken differential equations, they tell you, we're going to take a very methodical approach here, and we're going to do some very educated work here, but ultimately, I want you to know that what you do is actually you follow a step. First step is we're going to guess the form of x sub f, the forced response. We're going to guess the form, but it's an educated guess. It's not a dummy's guess. It's a very educated guess. And this is what we're going to say. We know that if this x sub f is going to satisfy this equation up here, then again, when I take the function and I take its derivative and I take its second derivative, somehow it's all going to cancel out and then get me f of t back. So we say that we guess that the form of x of f is the same form as f of t plus all of f of t's unique derivatives. Excuse me for a moment. I've got a phone ringing here somewhere. So plus all of f of t's unique derivatives. So that means I look at this function and I guess that it looks just like that, plus all of the unique derivatives of that function. Example of unique derivatives. Example of unique derivatives. So that we know what all this means. So when I look at the function, let's pretend f of t equals t squared. Well, the form of this function, here's the form. The form is a times t squared, where a is a constant. That's the form. But look at the derivative of f of t. The first derivative of f of t is 2t. Don't worry about the constant 2. Don't worry about the constants. It has this form. So now we've got to add to this. There's a bt term. Then let's see, I take another derivative. And when I take another derivative, I get 2. I get a constant. The form of this is a constant, plus c. Then I take the derivative of a constant, I get 0. And all those derivatives there on in are 0. So the form that I'm going to guess is going to look like this. That's an example. Let's say I had f of t was equal to 10 cosine of 3t. Well, over here, the first thing I'm going to guess is it's going to be a times cosine of 3t. It has that form. Now, what's the derivative of the cosine of 3t? Well, when I take this derivative, I get negative 30 sine of 3t. Well, I've got a sine term. So I guess b sine of 3t. But now what happens when I take the derivative of the sine? I get cosine of 3t again. Yeah, I get some other number out here, but the form of the function is cosine of 3t. I've already got cosine here, so that would be my guess if my function was 10 cosine of 3t. So when we say guess that it looks like the function plus all its unique derivatives, I take derivatives until I get to a derivative that looks like something that I already have, or till I get to 0. Okay, so that's step 1. Step 2, after the guess, then compute xf prime and xf double prime. Okay, compute both of its derivatives. So you take your educated guess and then you plug it in, right? So we're going to put that in. So 3. So keep in mind right now from step one, we have some unknown constants right now. And notice how I didn't use K1s and K2s so that we never confuse ourselves between what is the forced response and what is the natural response. So I used A's and B's. So we're going to compute xf prime and xf double prime, but we have these unknown constants. We compute that. Then we're going to substitute all 3 of those. Substitute xf, xf prime, and xf double prime into the differential equation. And we don't just substitute them in there for nothing. We substitute them in there to solve for all of these unknown constants that I was talking about. Well, all unknown constants in x of f. So right here we had, up above, I had A's and B's and C's. So here's an A, there's a B, so we have those. When we're done, we're going to solve for all of those so that the forced response will be completely known. So there's nothing that is unknown to us in the forced response. The only unknowns, the K1s and the K2s, are in the natural response. Okay, so we're going to do that, and we're going to solve for these unknown constants, That's what we have. Let me just pull this down so that you can read that. So what we're going to do is we're going to substitute those constants, substitute the constants back into x sub f. So we now have the full response for x sub f. We have the full response. So when we do that, we should have a completely known x sub f. Okay? I'm going to do an easy example today, and then we'll expand on this tomorrow because we're winding down on time. Here we go. X double prime plus 3x prime plus 14x is equal to 42. So the form of x of f, gosh, Dennis, spit your words out. So the forcing function f of t is 42. It's a constant. So we are going to guess that x sub f is a constant. And what are all the unique derivatives of 42? Well, the derivative, f prime, is equal to 0. So nothing interesting. So this is our guess. All right? So that's the guess. Now, xf prime is 0. xf double prime is 0. So those are my derivatives. Now take these three, substitute them in. Here we go. X double prime, 0, plus 3 times 0 plus 14 times a is equal to 42. All right? 14a equals 42. A equals 42 divided by 14, which is equal to 3. So our x sub f, the forced response, is equal to 3. Done. That was really easy. Yeah, I gave you an easy one. That was the case of a constant value. Some of them are going to be a little more challenging than that. I'll do a couple of other examples with that tomorrow. So basically what we have now is we've got a situation where we're looking at our total response. We've got the two pieces, and we're going to look at the total response. So we'll look at some more examples tomorrow of what we can have for different forced responses, what our guesses will look like, what might happen when we run into a problem, and why might we need to change our guess. So there are guesses that are educated guesses, and we want to be really smart so that we never make a mistake. In order to never make a mistake, we will always have to compute the homogeneous response first, and then we'll have to look at that and look at f of t when we are making our educated guess for what the forced response will look like. Okay, any questions about that right now? Give everybody a moment to open up, and you can unmute. Any questions about what we did today, where we're going?
No, none for me.
Okay. I think right now it's a lot of math.
Oh, no, sorry. I was talking to my niece. Sorry.
Okay. So right now it's a lot of math. That's what we're seeing. We've got a lot of math that's taking place. In terms of that math, I just want you to know the results of the math. The results of the math. Most of the calculus that we did, you won't have to do. We will need to know a little bit of calculus for the part that we just did, because when we make our guesses, we're going to have to take derivatives. But fortunately for you, I'm going to restrict our forcing functions to be within like one of 3, 4, 5 different categories. They will always be one of those, so they won't be other bizarre functions. So once we know what those categories are, our guesses will be pretty well known. So that way, we won't have to utilize very much calculus whatsoever in solving these problems. And that's my goal. I'm trying to stay away from as much calculus and focus much more on the circuit theory. So our time's up today. It was great seeing you or listening to you or peering through my computer at you. We'll do some more of this tomorrow and pick it up from where we left off. Have a great rest of your day. I want to continue to remind you, as I will every day, stay safe, stay away from people. I know it's real easy to kind of ignore what's out there, The news yesterday should be pretty staggering. A pretty young 25-year-old soccer player who passed away after contracting the coronavirus. This is not restricted to just old people. It is more likely to harm elderly people, but please stay safe. This is a dangerous virus. There's not a lot that's known about it. Please stay safe. Till then, I'll see all of you tomorrow. Take care.
You too.